All right, so the next thing is to understand that a separating hyperplane comes with margin, right? So if we have some separating hyperplane, then we can kind of move it to one side, move it to the other side, and the most extreme positions where our hyperplane is still separating, right? So they define these margins. So margins, and we can move it parallel to itself within the margins so that it still remains separating. Now we're going to try to find a separating hyperplane, so that is going to be first in the middle between its margins, and the margin size is going to be as large as possible. So basically we're going to maximize the distance between the two margins. So hypothetically, if say you consider a different hyperplane that is say between this margin and say this margin, well, no, it's probably not this one, something like this, then in the other position, the size of the margin would be smaller, all right? So what you see here is actually it has the largest possible margins. Okay, now a separating hyperplane is given by this linear equation. Now, since multiplying an equation by a constant does not change the hyperplane, right? So hypothetically, I don't know, if you have something like and then minus 5 plus x1 plus x2 is 0, then if you just multiply it by 2, so minus 10 plus 2 x1 plus 2 x2 is 0, is going to be a different equation that defines the same hyperplane. So which means that we can always divide everything. We can always multiply our equation by the sum of the inverse of the sum of the squares, 1w squared plus and so on, plus wp squared, well, square root of this. Okay, so we are going to normalize this equation. Well, and then if a separated hyperplane satisfies this condition, so the right-hand side is positive, then to make it extreme, to make the margin size as large as possible, instead of requiring it to just be positive, so which defines any separating hyperplane, we will want to require it to be as large as possible, so bigger than some number m. And we want to maximize this number m. Okay, so which is why the maximal margin classifier, so this is from some point of view is the separating hyperplane that separates the two classes as well as possible, right? So with a margin size that is as large as possible. So it is going to be the solution of the following optimization problem. So we are going to maximize this m capital subject to this constraint such that we have this inequality, right? So the idea here is that if our training point were exactly on this hyperplane, then the right-hand side would be 0, right? So for points that are far from the hyperplane, the right-hand side is positive, and the further they are away from the hyperplane, the bigger is the magnitude, right? So, and then basically we want it just to be as large as possible, and we are going to maximize this m, which sits in the right-hand side of this inequality. Okay, and this is going to give us the hyperplane with the maximal margin. Now, points on the margins, points that are exactly on the margins, are called support vectors. So this is important. So we're going to see support vectors more times, several more times today, and this is what the method is named after. So it is called a support vector machine. So they carry some special significance in the method. Okay, so support vectors are just training observations that are exactly on the margins. All right, so this is the end of the second part. Now please do the quiz.